Okay, so we're going to jump right in. If you had failed normality for the repeated measures ANOVA, but you still want to be able to say, are there differences between your three groups? You might switch to the non-parametric test. So you might switch to the test that doesn't require normal data, and that's going to be our Friedman's test. So for the Friedman's test, this is used to determine whether one group's ranking on three or more continuous or ordinal variables differ. So it's similar to a repeated measures ANOVA. You've got three groups, and those groups must have either continuous data or ordinal data. This test does not assume normality. You don't have to meet that expectation of normality. You don't have to do a Shapiro-Wilk test or a Komglen-Rath-Smirnov. You just have to have either continuous or ordinal data to use this test. And I've left you some help guides for if you're looking for a little bit of extra help running those tests. All right, so we're going to have to check a couple assumptions. Every test we have has certain assumptions that must be met in order for the results of the test to be valid. For assumption 1, our dependent variable must be either ordinal or continuous. So for continuous data, there are 3 data types in RStudio for that. int, which is integer, dbl, which is double, num, which is numeric. If you have one of those data types, you've met this assumption. You could also use ordinal data. So this is if you had, for example, Likert data. So if you've got the options like 1 to 5, you've got a neutral midpoint, you've got symmetry around that midpoint, and you're looking to say, are there differences based on some Likert data? You could do that, but it has to be listed as ordered factor as a data type. If you're just joining for the first time, you might need to run line 142. You might need to install the tidyverse package in order to run the next thing we're trying to do. I already have this on my computer. I don't need to run this. I've already run line 143 today, but I'll run it again. We're going to load the tidyverse library so we can use some of the functions in that package. And I'm going to take a glimpse at my data. And when I do that, it says glimpse of fake data. We have 30 rows and 7 columns, and it tells us which data type everything is in my data set. So I've got some int data and some dbl or double data. Our dependent variable, we're going to be using fake data 1, 2, and 3. These are listed as dbl, so we've met this assumption. So we've got our continuous data. We'd like to run this test. What do we do next? Well, assumption 2. The independent variable must be categorical with 3 or more related, matched, paired groups. There's different ways to say this, but you have to have, if I was a participant in the study, I need a score for all of my groups. So we can look at our data and have a look. In our fake data set, each row is a participant. So if I was a participant in the study, I have a score for fake data 1, fake data 2, and fake data 3. So we pass this assumption because each person has 3 related, matched, or paired groups. They have all 3. I've left you an expert tip here. Non-parametric tests do not care about outliers. So if you started with the repeated measures ANOVA and you removed a few outliers for certain reasons, you could, if you wanted, put those back in because this test actually doesn't care about outliers. This test is using medians where outliers don't matter as much as they do with the tests that use means. So it's up to you whether you would like to put those outliers back in. And that's it for our assumptions. It's pretty easy. We've got the correct data type. We didn't actually do anything with outliers, so we're ready to go. We can run the Friedman's test. So what we're trying to do, we would like to check whether the medians of fake data 1, 2, and 3 are statistically significantly different from each other. Are the medians different? We're going to need the RStatics package to make this work. So if you haven't already, you can run line 161, which is installed at packages, left bracket, quotation mark, RStatics, RStatix, and quotation mark and bracket. I already have this on my computer. I don't need to run this today. I can run line 162, which is library RStatics. I get some red text. It says attaching package RStatics. The following object is masked from package stats filter. This means the stats package and the RStatics package are fighting for what to do with the filter function. This is not an error code. It's not saying it didn't work. It's warning me that if I use filter, those 2 packages are going to fight, which is fine. If you get an error code either right here or in a minute saying you need the coin package, you will need to run line 164. So if you want, you can just run it now. And then that way you won't have that issue. It might ask you to install the coin package. Okay, so I'm trying to use the Friedman's test. What if I've never done this? I don't know what I'm doing. I can run line 166, which is question mark Friedman underscore test. and it will give me some output down here in our help window to help me figure out what I'm doing. It says Friedman underscore test. That's our function. Squiggle brackets are statics. That's the package the function comes from. And it says Friedman rank sum test description provides a pipe-friendly framework to perform a Friedman rank sum test, which is the non-parametric alternative to the one-way repeated measures ANOVA test. Wrapper around the function Friedman.test. To read more, there's a button you can click. Here's the usage. It has some arguments. There's some values you can give it, and it gives you some examples. Might look a little concerning. That's okay. We're going to run through this together. The thing that we care about is we actually need this data to be in long format. If you were just here for the repeated measures ANOVA version, we already did this. We already transformed the data into long format. And what I mean by long format is we need one column for the group. So it's going to say for some parts, it's going to say fake data 1. For some of them, it's going to say fake data 2. And for some of them, it's going to say fake data 3. We have a score for every person for each of those groups. And we have a participant column saying, are you participant 1, 2, or 3? And each participant has a score for fake data 1. They also have a score for fake data 2. And they also have a score for fake data 3. So that's what we mean by long data, going down the page. So if you need a review for that, you can watch the repeated measures ANOVA video if you're following after the fact. To run this, on line 169, we have Friedman underscore test left bracket, fake underscore data underscore score, tilde, fake underscore data underscore group, that's straight vertical line, participant, comma, data equals fake underscore data underscore long. We need the long format data for this. So what this is doing is we're saying, here's your dependent variable, here's your independent variable, here's what we're doing for our error term, here's the data that we need. We can highlight this and click run, and it will give us some output. It says we have a tibble, a 1x6 tibble. It's just a data type in RStudio. Don't worry about that part too much. It says you're going to look at the scores. Our n, or our number of observations, is 30. It gives you a statistic. It gives you your degrees of freedom for that statistic. It gives you a p-value. And under method, it tells you what test you ran. That's the Friedman test. So the thing you probably care about the most here is the p-value. Our p-value says 9.36 e negative 14. It means take that decimal place and move it 14 times to the left. So it's going to have a lot of zeros. So our p-value, let's see if I can read it, is 0.0000000000936. That means there is a statistically significant difference in the medians of fake data 1, fake data 2, fake data 3, and that difference is somewhere between those groups. We don't know where. We're going to have to follow that up and ask in a second, where is the difference? But somewhere in there is a difference. You might want to report the effect size for the Friedman's test. The effect size is called Kendall's W, and we can get that using the Friedman underscore F size function. You give it essentially the same thing you just gave it for the Friedman's test, but now you pass it to the function Friedman underscore F size. So Friedman underscore F size, left bracket, fake underscore data underscore score, tilde, fake underscore data underscore group, the straight line, participant, comma, data equals fake data long. I can run this, and it says you're checking score, your n is 30, here's your effect size, here's your Kendall W, and it was a large effect size. So it gives you a little bit of extra information. And if you wanted to write the results, you would do so like this. Oh, we've got some question marks in there for some reason. Interesting. So this should be for your Friedman's test. I don't know why it's given us some question marks. So you've got your Friedman's test. You put your degree of freedom. You say, this was my statistic for the Friedman's test here. You give it the p-value. You can give it the Kendall's W, which is the effect size, so that people know how big was this effect. That's how you would write it. The next thing you might want are your medians, because you've got 3 groups and you're saying the medians are different somewhere, so you might want to tell people what those medians are. So I can just use the median function on all 3 and click run. The median for fake data 1 is 87.1945. The median for fake data 2 is 92.14947. And the median for fake data 3 was 112.7586. So you can write that out as well if you want. It's also a good idea to visualize your data. The best visualization for a Friedman's test is a box plot. because the Friedman's test deals with medians. So it's not a graphing exercise today. You can just run the line if you want. We can cover it if you have questions afterwards, but we're going to do a box plot. It looks a little squished, so I can click the zoom button to make it a bit bigger. So we've got medians on our y-axis, and on our x-axis we have fake data 1. We have a median and interquartile range, and then our whiskers. We've got fake data 2, median, interquartile range, and whiskers. And we have fake data 3, median, interquartile range, and whiskers. The medians and the graph do not tell you which groups are different. You might be able to look at this and think you know which groups are different, but you still have to run the follow-up tests to say statistically which ones are different from each other. My guess is fake data 3 is going to be different because look how high this is compared to everything else, but the graph is not enough to draw that conclusion. So we're going to do some post-hoc testing. So if you found a significant Friedman's test, if your p-value was less than 0.05, it means there's a difference somewhere, and you need to follow that up with additional testing to say where are the differences. So we found a significant Friedman's test. We're going to follow that up with some Wilcox and essentially non-parametric t-tests. So we're going to use Wilcox underscore test. We're going to say fake underscore data underscore score tilde fake underscore data underscore group. Data equals fake data long. Paired equals all caps true. p.adjust.method equals in quotation marks Bonferroni. What this is doing is saying this is our dependent variable, this is our independent variable, this is the data set we're trying to use. It's paired data because it's repeated data. I'm a participant, I have a score 1, 2, and 3. And we're going to make an adjustment, the Bonferroni adjustment, because we're doing 3 tests at the same time. So I can highlight this, I can click run, and it gives you the results of all 3 tests. It says which groups are different from each other. So we're looking at the score variable, and fake data 1 versus fake data 2, we have a p-value, which is right here, the adjusted p-value, and it gives you some stars to say whether that is significant. You would generally report the adjusted p-value because that's saying I ran 3 tests. I don't want to make a mistake by accident and say something is significant if maybe it's not. I'm going to add a Bonferroni adjustment to make it less likely for me to make a mistake. So the p-adjust column is normally what you would want to report. So we've got our p-values here. Fake data 1 is significantly different than fake data 2. Fake data 1 is significantly different than fake data 3. And fake data 2 is significantly different than fake data 3. We know they're significant because the p-values are less than 0.05. So we can say there is a difference in the medians between 1 and 2, between 1 and 3, and between 2 and 3. If the p-values were greater than 0.05, all we would be allowed to say is we failed to find a difference between the medians of those groups. I didn't say there's no difference. I say we failed to find a difference, and that's a very specific little stats thing for you. But that is how you do the Friedman's test.